Two-stage turbine with reheating and without reheating. For this part is without reheating. So from here, now gas turbine cycle with two-stage turbine. The reason why we increase the number of stages is to improve the cycle efficiency of the gas turbine engine or the gas turbine cycle. This diagram here shows you 3 or 4 devices here. One is the compressor, which is used to take in air from the ambient or from the surroundings. And then it undergoes a full isentropic compression. The pressure and temperature is being raised when it goes into the compressor. Now, then after that, it goes into the combustion chamber where the air and fuel mixture ignites. Then after that, the hot gas will go into the first turbine, which we call the high pressure turbine. Now, the high pressure turbine here is used to drive the compressor. And then it goes to the second stage turbine, which we call it as low pressure turbine. So again, it will undergo isentropic expansion, and then it drives a generator or a propeller. So based on that, when you look at state point 1 to 2 prime, the air would have undergone an irreversible process due to internal friction. State point 1 to 2, where it will undergo isentropic compression. Then from state point 2 to 3, it will undergo a constant pressure heating. 3 to 4, again here, it will undergo an isentropic expansion to the high pressure turbine. Then the next would be state point 4 prime to 5 prime or 4 to 5, which is the isentropic expansion to the low pressure turbine. Okay, so that is a two-stage turbine. We might have two-stage with a reheater, or you can have a two-stage compressor with an intercooler, and then you can have a regenerator. So first of all, let us take a look at the work output from the high pressure turbine. So that is this. So the high pressure turbine actually generates work. So you have work output from the high pressure turbine. So I put a subscript HPT here, represents that is the work out for the high pressure turbine. So the work output of the high pressure turbine is used to drive the compressor. So whatever work output you have for the high pressure turbine, please equate to the work input of the compressor. As from the diagram, you can see the high pressure turbine is only driving the compressor. So therefore, we can say the high pressure turbine work output, okay, is equals to the work input of the compressor. Unless, if let's say there is a mechanical efficiency that is given due to frictional loss, let's say 2%, then let's say your mechanical efficiency will be 98%. So actually this one is the other way around. So the work output here times mechanical efficiency, the work output of the high pressure turbine multiplied by the mechanical efficiency would be equals to what is received by the compressor. That is the work input. So this one, put it the other side. Okay, so this is my mistake again. So the work output of the high pressure turbine is equal to CPG. It refers to the gas. Now you have two ways of solving problems on gas turbine cycles. One is using what we call, okay, relative pressure, which is only applicable for any of the isentropic process. So the isentropic process actually appears in the compressor, high pressure turbine, and the low pressure turbine. So here you have isentropic compression, isentropic expansion, and isentropic expansion, which you can use relative pressure. But for the time being, we are using this by considering that the CPG is a constant, okay, constant throughout the entire, okay, expansion or the gas side. So you have CPG multiplied by the temperature difference between 3 and 4 prime. Then the work output from the low pressure turbine, again from here, you will have 4 prime to 5 prime, or you can see we are using CPG here, means we are referring to gas. All these device or components here, we are looking at the gas side. Okay, so multiply by the temperature difference of T4 prime minus T5 prime. Relative pressure for the work output of the low pressure turbine. There are two ways, but we are using this by calculating, okay, the work out of high pressure and low pressure by taking CPG multiplied by the temperature difference. Then you have work input in the compressor, which is CPA. So this is a specific capacity at constant pressure for A. So that is T2 prime. This is the actual gas turbine cycle. It's not the ideal gas turbine cycle. If ideal gas turbine cycle, you straight away take T2 minus T1. Okay, T2 prime, which is the actual state point after the irreversible process. So for any isentropic components here or devices here, we can use another method which we call relative pressure. Okay. So and then this would be the heat supply from the combustion chamber. So which is CPG T3 minus T2 prime. That is the temperature difference here. And remember, okay, so based on the schematic diagram, we can see the high pressure turbine is driving the compressor. So if let's say mechanical efficiency is included, then you will have to take, okay, or you can calculate work in, okay, by taking work out times mechanical efficiency, okay, for the high pressure turbine. And then for the power output part, we only refers to the low pressure turbine where it drives the generator, or in this case, it's just driving a propeller. Okay, so if mechanical efficiency is given, so that means you are taking into account the frictional loss due to, okay, the loss due to friction. Okay, now because of the shaft transmission here, usually or most of the time you have friction loss. You have friction loss. So therefore, that is why we have to consider, okay, the mechanical efficiency. So the net power output should be the work output of the low pressure turbine multiplied by the mechanical efficiency. For the work input here, you can take mechanical efficiency multiplied by the work output of the high pressure turbine. This was my mistake. Okay, so the net work out, okay, should be based on 4 to 5 prime, that is the low pressure turbine, which is CPG T4 prime minus T5 prime if mechanical efficiency is given. So we have to include, then we have to multiply by mechanical efficiency. So for the TS diagram, you can see here, first from state point 1 to 2, where the A undergoes an isentropic compression. So you can see actually the pressure and temperature. This is the pressure line. So the pressure increased and the temperature is increased also. Okay, it's also increased. So that is the isentropic compression. So due to the irreversibilities, you have 1 to 2 prime. Okay, then from 2 prime, this is the actual state point for an actual gas turbine cycle. 2 prime to state point 3 here is your constant pressure heat addition from the combustor, in the combustor or the combustion chamber. Then from 3 to 4, you can see this is isentropic. This is not isentropic, yeah. This is your isentropic expansion, 3 to 4. Then due to irreversibilities, you have 3 to 4 prime. Then we continue from 4 prime, not from 4 to 5, yeah. We continue from 4 prime to 5 after that for actual gas turbine cycle. 4 prime to 5, which it goes into the low pressure turbine where it undergoes isentropic expansion. And due to irreversibilities, you have 4 prime to 5 prime. And then it goes out from there and then it reaches a stage, okay, the exhaust gas from the low pressure turbine. Okay, so this would be a TS diagram for actual gas turbine cycle. You can see we don't connect the last point to the initial point 1. Okay, so this is an open gas turbine unit. Unless you are referring to an ideal gas turbine unit, then this line you will have to draw from 5 back to 1. For ideal gas turbine cycle, you don't have 5 prime, 4 prime, and 2 prime. You straight away you will have 1 to 2, 2 to 3, 3 to 4, and then 4 to 5 straight away down, and then back to 1. That is the ideal gas turbine cycle. Okay. So remember the isentropic efficiency for compressor, that's this part here, the head, and then you can use the isentropic compression or the isentropic relationship to find the temperature T2 by applying this. You cannot apply this for 1 to 2 prime. Please do not. Okay, then you have for the turbine, the isentropic is 3 to 4, not 3 to 4 prime. So that is why when you look into this equation, it's between 3 and 4. Okay, 3 and 4. Then the isentropic efficiency, remember for turbine, is actual over theoretical. Then for the low pressure turbine, from 4 prime to 5 is isentropic, not 4 to 5 like this, yeah? Or not 4 prime to 5 prime. It's 4 prime to 5, that is the isentropic process. So you have the isentropic relationship here between 4 prime and 5. That is where you see the vertical line. Okay, so the constant pressure heat rejection have to remove. Okay, you have heat rejection actually, because for actual gas turbine cycle, usually the exhaust will goes to the atmosphere. Okay, so that's all for this section, this slide, okay, or this video, and thank you. Yeah, this would be part 5, but it is still on theory side. Yeah, now two-stage turbine with reheating. So this will be two-stage turbine. We are looking at a two-stage turbine with a second combustor. A second combustor. That means a second combustion chamber. So this will be the cycle where you have A intake here. So it will undergo isentropic compression in the compressor, where the pressure and temperature will increase. And then after that, the hot air now will go into the combustor. where you have fuel injected, and then what happens is the air and fuel mixture here will ignite, and at constant pressure, heat supply. Okay, so then this hot gas will go into the high pressure turbine where it undergoes isentropic expansion again, and then from here's mistake here again, and then from here the work output of the high pressure turbine is used to drive the compressor. So I remind you one more time, the work output of the HPT, you should equate it to the work input of the compressor. So sometimes when mechanical efficiency is given, you have to take work output of HPT multiplied by mechanical efficiency, and then only equates to the work input of the compressor. Then this isentropic expansion through the HPT, after isentropic expansion, it will goes into the second combustor, where the hot gas is being reheated to its initial temperature, that means here, or sometimes or otherwise stated, okay, or otherwise stated. So from here, it will undergoes another constant pressure heating process before it is sent to the low pressure turbine. So in the low pressure turbine, again, it will undergoes a full isentropic expansion, okay, and then coming out at state point 6. Now, due to irreversibilities, you have 6 prime, 4 prime, and 2 prime. Okay, if you were to refer to only isentropic compression, then you have 2. Isentropic expansion, then you have 4. Isentropic expansion LPT, you have only 6. These are only considered when you take the irreversibilities into account, and especially in open cycle, open gas turbine unit. And remember, I remind you one more time here, work out times mechanical efficiency equate to work in compressor. So here I don't have to explain anymore. This is state point 1 to 2 actually, isentropic compression. Then 2 prime or 2 to 3, which is the constant pressure heat addition here. Okay, then you have state point 3 to 4 prime, the isentropic expansion, 3 to 4, okay, HPT. And then you have the state point 4 to 5, that is another constant pressure heating, and we call it as reheating. That means that is the second combustor or the second combustion chamber. Then the state point 5 to 6 would be your isentropic expansion through the low pressure turbine. So work in from the compressor, as you know, okay, CPA, that means because compressor is A side, the first combustor, the HPT, the second combustor, and the LPT, all is in the gas side. Okay, this part here is all in the gas side, and this is on the A side. So you can use CPA here. Okay, so for any isentropic processes like compressor, HPT, and LPT, you can use another way of solving the problem. Okay, and then the table it can be found from the textbook Yunus Schengel, okay, or the table which, okay, the second table, okay, which you can find out the enthalpy based on the relative pressure. Okay, so that is your work in. Then your heat supply, so you have CPG T3 minus T2 prime. And then 3 to 4 prime, which is the high pressure turbine, CPG, okay? T3 minus T4 prime between this, okay? And then work net, okay, or work output. The net work out or the work out, you can see this one is only driving this. Now, it's not driving the combustor, yeah, please, okay? It is only driving the generator or the propeller here. So the net work out basically is based on the LPT only. Okay. Now, if let's say, for example, you want to find gross work expansion, then you will have to take this work out plus this. If it is gross work expansion, then you will have to take the work out of the HPT plus the work out of the LPT. Okay, if let's say, for example, you want to find net work out, okay, you can use this method as well. The work out of the LPT plus the work out of the HPT minus the work in. Okay, the work out of the LPT plus the work out of the HPT minus the work in of the compressor. So since the work out of the HPT is equals to the work in of the compressor, so it will cancel out. So the net work out is basically only the work out of the LPT. Okay. Then for the TS diagram, the previous, when you don't have reheat, okay, you don't have this section here on the tail. Okay, so when there is a reheat, you can see from 4 prime, previously from 4 prime you go down vertically downwards isentropically to state point 5. Okay, from 4 prime to state point 5, where you don't have this section here. Okay, only with reheating you can see this part here. So from 4 prime to 5, it's not from 4 to 5. Your actual state point is 4 prime, 6 prime, and 2 prime. Okay, for open gas turbine unit. Closed gas turbine unit, you don't have 6, 4, and 2 prime. So straight away you continue from 4 to 5 like that. Okay, so here you can see there is another heating taking place here, 4 prime to 5. Okay, so then it undergoes isentropic expansion. This would be your low pressure turbine LPT. And if you consider the irreversibilities of within the turbine, so you have 5 to 6 prime. Okay, that's your TS diagram. And this would be the isentropic efficiency for 1 to 2. Remember, isentropic is here, yeah? So you can write here T2 prime over T1. You take a look at your TS diagram, what you have put here. If you have put here a 2 prime and this is 2, then this will be 2 prime. Okay, but I have put here as 0.2, and then the actual points are always accompanied by a sign here. Okay, so therefore, okay, for this you only consider T2 to T1. Okay, this one, the vertical line here. And for this also the same thing, between 3 and 4, and this one is between 5 and 6. Okay, 3 and 4 for this. Okay, 5 and 6 is for this. Okay, and then you have the isentropic efficiency for both HPT and LPT. Remember, actual is here over theoretical. This one, the actual is here over the theoretical. For the compressor, the actual is here and the theoretical is here. So for compressor is theoretical over actual. Okay, that's for the second section. Thank you and stay safe. Okay, see you in the next video. See you in the next video. Bye bye. So we'll be looking at problem solving. So this would be the first example. Okay, the first example for two-stage turbine of a combustion of a gas turbine open unit. Now, in a marine gas turbine unit, a high pressure stage turbine drives the compressor, and a low pressure stage turbine drives the propeller through suitable gearing. Now, the overall pressure ratio is 4 to 1. Now, the mass flow rate is 60 kg per second. The maximum temperature given is 650 degrees C. And the air intake conditions are 1.01 bar. The air intake, that means the state point 1 pressure. And then the temperature is 25 degrees C. Now the isentropic efficiencies of the compressor, high pressure turbine, and the low pressure turbine, they are 0.8, 0.83, and 0.85 respectively. Now the mechanical efficiency of both shafts, that means the shaft that is between the high pressure turbine and the compressor, and another shaft that is between the propeller and the low pressure turbine, both the shaft is at an efficiency of 90%. Now that means there is a 2% loss due to friction. So therefore, any workout output that we consider, we should multiply by its mechanical efficiency. So neglect kinetic energy changes and assuming CPA 1.005 and CPG 1.15, if I'm not mistaken. I have left out that part. Okay, so that is constant specific heat capacity. So calculate the first part, the pressure between the turbine stages, the cycle efficiency, and the shaft power. So this would be your two-stage turbine without a second combustor. Yeah? You have only one combustor. Okay, so I should put 1, 2, 3. But then in this diagram, it shouldn't be any problem. 1 to 2 prime, 3 to 4 prime, and 4 prime to 5 prime. But then when you consider the isentropic compression, that should be 1 to 2. Then the isentropic expansion of this should be 3 to 4. And then this one should be 4 prime to 5. Okay. So this would be the TS diagram, which I have drawn nicely here. So this is where you have your heat supply. So this would be your isentropic relationship between the pressure and temperature. So you can see here I put gamma minus 1 over gamma. Okay, if you move this to the other side, that means to the left hand side, it should be power of gamma over gamma minus 1. Okay, so, and this would be your isentropic efficiency for the compressor. Remember, theoretical over actual for compressor. Okay, and then for the turbine, okay, so that is the isentropic process. So that should be your isentropic efficiency should be actual over theoretical, and this one actual over theoretical. The isentropic relationship should be between 4 prime and 5, 3 and 4 here. Okay, so that's what I have written down here. So first thing is, now what we need to do is to find out the temperature of T1, T2, T2 prime, T3, T4, T4 prime, T5 and T5 prime. But okay, the temperature at the suction intake, that means the compressor inlet here, is given. Okay, the temperature is given at 25. So 25 plus 273, you have 298 Kelvin. So you have 298 Kelvin. And then the highest temperature is given 650. So plus 273 should be 923 K. So what we need now to find here, the temperature T2 first. Okay, temperature T1 is given. So we find temperature T2 by considering the isentropic compression of state point 1 to 2. For any isentropic process, the isentropic relationship between pressure and temperature, you see is slightly different from this. Yeah, this one I purposely put it, move the power here towards the left hand side, so it is inverse. Okay, reciprocal. So that is why it's gamma over gamma minus 1, and it is not gamma minus 1 over gamma. Purposely, so that you know, okay, what happens when you put the power here towards to the temperature side, and what happened in the pressure side. So this will be your pressure ratio 4 to 1. So that means this pressure line here is 4, and this pressure line here is 1. Okay, so 4 to 1. And they have given us the inlet pressure is 1.01. So the inlet pressure here 1.01. So the pressure here should be 4.04, like that. Okay. So using the isentropic efficiency, isentropic relationship, we will be able to find out the temperature of this T2. So now to find out the temperature of 2 prime, then let us consider the isentropic efficiency for the compressor, which is 0.8 here, 0.8. So that is your isentropic efficiency for compressor. So I put it in short, okay? Your subscript here, isentropic efficiency for compressor 0.8. Remember, it's theoretical divided by its actual. So from this, we will be able to find the temperature T2 prime, this one, okay? So now, then after that, and we know that, okay, the work input of the compressor is CPA T2 prime minus T1, right? And it is equals to the work output of the high pressure turbine. So we can actually equate the work input of the A compressor equal to the mechanical efficiency multiplied by high pressure turbine. There is no other devices that it is driving for the HPT unless it's stated in the question. Okay, so the question say the low pressure turbine drives the propeller. That means at this part here, not here. Okay, so this is HPT. So taking the work out of the HPT multiplied by mechanical efficiency is equals to the work in of the compressor. So work in CPA, remember for the compressor side, CPA. So we assume CPA as 1.005. Okay, actually this can be also found if you have a relative pressure method. Okay, if you refer to Schengel textbook, okay, it is showing you another way, okay, which both these will give you the same answer. Now T2 prime minus T1. So you got your work in as 181 here, 181.94. Then for mechanical efficiency, you have, okay, we don't have to go into this definition of this mechanical efficiency here. You just need to remember, okay, the workout that we have, okay, if we multiply by the mechanical efficiency here, this mechanical efficiency here, then it is equals to that will be equals to the work in of the compressor here. Okay, so you have work out of the high pressure turbine. So we have found this, okay, the work out of the high pressure turbine. Okay, then now what we have is we can take this value here, 185, equate to CPG T3 minus T4 prime, where T3 is 923, given in the question is 923. So that is our subject, T4 prime. So from here we can find T4 prime. So it is equals to 761.6 Kelvin. Okay, so we got T4 prime here, but we haven't got our T4. So we can use isentropic efficiency for the HPT to find out T4 actually. So based on isentropic efficiency of the high pressure turbine, so we have actual T3 minus T4 prime over the theoretical T3 minus T4. So you have temperature T4 now is found is 728.5 Kelvin. Then, based on the pressure ratio, they have given us pressure ratio, this pressure line here, to this pressure line is 4 to 1. 4 to 1. So between P3 and P1, that means now, not necessarily is P3 and P1. It can be P3 and P5, okay? Or P3 and P5 prime, or P3 with P1. This will give you the same pressure ratio 4 in the question. Question is say the pressure ratio is 4. So we know P1 is 1.01, so we can find out P3 pressure 4.04, okay? So after that, based on the isentropic relationship, okay, so you have this, okay, between pressure and temperature. So we can find out the first part of the question. They ask us to find the outlet of the pressure of the outlet of the high pressure turbine. Both of these are actually outlet of the HPT. So they want us to find this pressure here, this pressure. Okay, so found, and it is equals to 1.567 bar. Okay. Then the next part is take point 4 prime to 5 here. Okay, this is isentropic, so you can consider your isentropic relationship again to find out your T5 here. So once you have found your T5, use isentropic efficiency of the low pressure turbine. Okay, use the isentropic efficiency of the low pressure turbine. I think I have left out that part. Okay, with the T5 prime. The T5 prime, if you want to find the temperature at T5 prime, you can consider the isentropic efficiency here, which is 0.85. 0.85, okay, equals to T4 prime minus T5 prime divided by T4 prime minus T5. You will be able to find out your T5 prime of 694.3. Now, it has been omitted, sorry, okay. So now it's shown here, sorry, yeah, it's shown here 694.3. 694.3 is shown here. Okay, so P4 and P4 prime is actually the same pressure because they are lying on the same pressure line. Okay, so part 2, they ask us to find the heat supply first. They ask us to find what? Ask us to find the cycle efficiency, right? So you can find out the heat supply. Okay, the heat supply is based on the combustor. So remember, it's CPG T3 minus T2 prime. So we have got our T3 here. So that is why I said tabulate all the values that you have got. Okay, it's better to do so. Okay, so this would be your T2 prime. So this would be your heat supply. Then your net work out, okay, should be based on this, yeah? Should be based on this. Or if you don't want to use this, or you want to know why, so you take the work output of the low pressure turbine plus the work output of the high pressure turbine minus the work input of the compressor. So you will have the net work out is actually equals to this only. Then multiply by the mechanical efficiency, remember 0.98, to find out your net work out. So net work out over heat supply give you the thermal or the cycle efficiency of the gas turbine cycle open unit. So the cycle efficiency is 14.86%. Then the next part, they ask us to find the power net. So based on the work net multiplied by the mass flow rate, which is given in the question, 60 kg per second. So you'll get a power net output as 4551 kilowatts. Okay, that's the first example. And thank you. Stay safe. Bye-bye. To the second problem solving, second example for two-stage turbine. So a gas turbine unit takes in air at 17 degrees C and 1.01 bar and a pressure ratio of 8:1. Now, please bear in mind, the greater the pressure ratio and the greater the adiabatic index, okay, the greater the difference in the pressure ratio, the greater will be, the higher will be the efficiency of the gas turbine unit. Now, the compressor is driven by a high pressure turbine, and the low pressure turbine drives a separate power shaft. The isentropic efficiencies of the compressor HP and LPT are 0.8, 0.85, and 0.83 respectively. Calculate the pressure and temperature of the gases entering the power turbine. The power turbine is your low pressure turbine. Yeah? The net power developed by the unit kg per second mass flow rate, the work ratio, and the cycle efficiency of the unit. So this part here, we are looking at basically the work ratio. Okay, so the previous example, we don't have work ratio. Yeah, so the maximum cycle temperature is 650 degrees C. For compression process CPA, so this is CPA, 1.005, and the adiabatic index, okay, that is the ratio. Adiabatic index is actually the ratio of the specific heat, okay, ratio of specific heat. Okay, so it's 1.4. Now for the combustion process and for the expansion process, this one are for the compression, that means the A side. Then for the expansion process, that means the gas side, the CP is 1.15 and the gamma is 1.333. So neglect the mass of field, neglect the mass of field. So same thing here without second combustion chamber. Second combustion chamber will be in our further problems solving. So now this is the TS diagram. So this slide here, I will go slightly fast because this one is almost the same as the previous one. The only thing is we have to find out the work ratio here. This is for you to have some practice. Okay, second example here, so you can do some practice on your own. Okay, so this would be the isentropic compression based on the compressor. So remember, relationship must be the vertical line here. Okay, so you will be able to find out T2 525.32 with your proper pressure ratio. Remember, pressure ratio different from the previous one, and this is 8 to 1. So this one basically is higher than the previous one. The previous one is 4 to 1. This is 8 to 1. And then let us compare the cycle efficiency afterward. Okay, so then when you consider the isentropic efficiency for the compressor, okay, you can consider this. So you will get your T2 prime of 584.15. So unless you have referred to my previous video, then when it comes to this video, okay, you will understand what I have said. Okay, so because I will be going a bit faster. Okay, so then this work in here, okay, so that is based on the compressor. So you have CPA minus T1. CPA, remember, for the A is 1.005. So you got your work in as 295.62. Okay, you got your work in for the compressor is 295.62. So and then for the work output of the high pressure turbine equals to the work input of the compressor. So you can take work output of the high pressure turbine multiplied by mechanical efficiency equals to the work in of the compressor. Did the question give us any mechanical efficiency? I think no. So if they have not given us, then the mechanical efficiency we consider 100%. That means 1. Okay, 1 times work out equals to the work in. So you will be able to find out T4 prime. So that is this temperature here. Okay, so then the isentropic efficiency of the high pressure turbine. So this tail here. Okay, so remember actual is 3 minus 4 prime, theoretical is 3 minus 4. So it's actual over theoretical, and it is given as 0.85. So T4 is 620.57. Then the pressure ratio is 8, so we know that this pressure probably will be 8.08 because the pressure ratio is 8 to 1, and then they've given us a pressure here 1.01. So definitely this pressure here will be 8.08. So the isentropic efficiency for the high pressure turbine, from there you will be able to find out the inlet pressure, the exit pressure of the high pressure turbine, the exit pressure of the HPT, which is 1.65 bar. This pressure here is 1.65 bar. This is 8.08, and this is 1.01. Okay, so based on the isentropic efficiency of the low pressure turbine, we will be able to find out the T5. Okay, then for T5 prime, again consider isentropic efficiency for high pressure turbine. Then you will be able to find out T5 prime. So once you have found out all the temperatures, okay, then you can proceed in calculating the work in, heat supply, and work output. Work in we have calculated. So list down all the temperatures for the convenience of our calculation later. So basically, this would be your T4 prime. Okay. So power net, remember power net is your network out, okay, multiplied by mass flow rate. So before finding out power net, so we must find out the net power output, the output of the low pressure turbine multiplied by mechanical efficiency, which is 1, which is not given, so we assume 100%, okay, which in real life you won't get 100%. So CPG T4 prime minus T5 prime, that is your power turbine. So your net out will be based on your power turbine. So you get a 73.36 kilojoules per kg. That is your network out. Then for the power net, okay, so network out multiplied by mass flow rate. So they say per kg per second of mass flow rate. So that is why we multiply by 1. So you get power net of 73.36 because they gave us the mass flow rate as 1 kg per second. Okay, so gross, remember gross work, as I've explained, please add up both the turbine work, the low pressure turbine work and high pressure turbine work. So you get a gross work expansion. So this will be CPG T3 minus T4 prime plus CPG T4 prime minus T5 prime. So you get this here. So this will be your gross work. So your work ratio should be net work over gross work. So you get a work ratio of 0.1986. Then for the cycle efficiency, we need to find out the heat supply. Okay? Remember, combustion chamber is in the gas side. So that is why this is CPG. So this is your heat supply, and then this is your cycle efficiency of 18.83%. I think it's slightly higher than the previous one. Okay, the thermal efficiency here can be increased, or the cycle efficiency actually can be increased by increasing the pressure ratio. Okay, and it totally depends on the pressure ratio, one thing. The second thing is the ratio of specific heat. That is your adiabatic index. Okay, so we can work out based on different pressure ratio, okay, to see or to compare what is the difference in their cycle efficiency. Okay, that's all for today. Thank you and stay safe, everybody. Bye bye. See you in the next lesson.